Ba-bam, ba-bam, bam, ba-bam. All right. All right. So we were at rainwater trapping. Hello, hello, hello. All right. So let's go for the Excali draw. Every time that happens with me. All right. And we will go with the rainwater. Trapping issue, right? Given an non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. So before than that, we have made we have made an Excel sheet. Excel sheet for uh, the approach of whatever question we are solving. So we will add that first. Let me show you. So container with the most water, we have solved it yesterday. Okay, so I will add this question there. So we have solved this container with the most water. Does it? Yeah. And in here, what I have done is iterating both the pointers, took the minimum height, okay, from left or right, and then uh, got the area and got the maximum area we got. Okay, so I guess use two pointers, l- left and right, iterate over the container, get the area of the container, get the max max maximum area, max area of the container forming while iterating over the container, get the max area with minimum height either from left or right. Just a second, guys. Hello guys. Hello, hello, hello. Hello, 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 hello. What the fuck is this? All right. So the question is now, given a non-teacher representation and elevation map, the width of each bar is 1. Compute how much water it can trap after raining. Height is this. Output is this. So we will follow the same rule to iterate uh, uh, from left and right. Okay, so let's start with that first. Int of left 0, int of r equals to height h gst dot length gth minus 1. All right, while left is smaller than right. Okay, so what we need is we need to check that uh, is there any case building up where we can store or contain that water and that water is not spilling uh, both the sides. Okay, so in this case, in the zeroth index we see that there no water can be stored because there is no wall before than that. We have a element of height 1, but that won't help because this water will spill that way. Okay, so we need to uh, keep a check of that, and then we'll see what what we can get. So what I am thinking is, let's have this image. All right, let's have this. Let's say each block equals to 1 unit. Okay, so on the zeroth index, say on the zeroth index, we will be having 0 water. In this, in the first index, we will be having 0 again. Uh, let's just copy paste it. Okay, and at this time, we will be having how much? We will be having 1. Why there will be 1? Why this will contain 1? This will contain 1 because there is a block present left or right, both sides of it. Okay, of uh, greater than or equal to height of 1. Okay, so 1 is present here as well, and 1 is present here as well. Alright, so that's why we got a unit block where water can be stored, right? uh, so in that way, let's go. So at this place we will get 0. On this place we will get again 1, as you know. Why 1? But our logic doesn't say that we will get a 1 until and unless we have a second wall, like on the opposite side. So there is no wall present here. So in that case we need to look back here as well. Is there any wall present? Yes, there is one wall, but it is smaller than this. Okay, smaller than the current height. So this water will spill over. So that's why that won't help. And in that case, the water we will be storing here will be 0. Okay, but here, if we see a wall greater than this one. So its height is greater than this one. In this case, we can have water get stored, okay, but not only here, because in that case we need to have some logic built up to get this water uh, contained here. So let's see what logic we can prefer. Hmm. So in this case, I will add 0, okay, because from our logic it's becoming 0 here also, because we are checking both the sides first. So what we can do is we can go both the ways, left and right. Let me just delete this one, not this one, brother. This, let me have this array as well. Okay, have I started this? To start this time. Okay, so each block is this. We got the GHT equals to this. You really need to visualize this, because from just numbers you won't get it. Okay, because from just numbers you can get this part, but not this one. Okay, all right. So 0 1, that is, then we have 1. Okay, then we have 2 and 1. We need to have 0 1 0 1. So we need to keep a track that which, so let's say if I have a left pointer, all right, let's say if I have a left pointer, let me just make it more bigger. All right, that works. How it get moves? Okay, so we have this one, okay, and here we have a left pointer and a right pointer. Okay, now uh, we need to keep a track of the uh, mm, let's say maximum left or minimum. We will need to have a minimum left first. Okay, so minimum left. Why minimum left? Because we need to uh, track the height. Like at this place it is 0, then at this place it is 1. Okay, so which one? No, the greater height, I would say. Yeah, so which one is greater? This one. So we will update this height. Okay, and we will we will like decrease this, not decrease, I mean subtract this height with this one. Okay, and in that case we will get 0, obviously, because this is just a 0 and this is 1. Okay, and then we will go with this uh, 1. Then we got this 0, it is smaller, then we won't do anything, and at that place we will be getting the height of 2. Okay, which is greater than this. So we will minus this and we will get the remaining height. Okay, and in that case we will get the height of we will get this water containing thing. So how uh, what I'm thinking is we will see left height equals to math dot max, or let's just say max of left end height of left. Okay, so in this way we will keep a track of its height. We will keep the track of its height. Okay, and we can iterate it over the array. Okay, and I think if I will just keep one pointer, it will be enough, right? Because we need to go it once and not from here and there. So if this, then this, then this. So if say, let's say I have L here, okay, we'll be having 0, 0. We'll be having this. Let's try coding this part. Okay, I think we need two more pointers of max L, which is 0, and max R, which is 0 as well. Okay, maximum left and maximum right, and let's go with the thing, and one is the count in 0, max left and max right. Just a second, guys. But we got this. So we will be adding this, but we want to be able to add this one, or we will add these two as well. So max left equals to math dot math.max maximum and but this one height as well. Okay, and we will see if, and we will add it to the count plus equals to not before. We will add this in the end. Max, let's say what will happen if height is smaller. So in this case we will get 0, 1, then 0 again, and then we will get this is 1 plus 1 plus 2 plus 1. Math dot absolute of what we had previously and what we have now, max of L. Okay, then we will be uh, doing this count. Okay, and the same we will be doing, but wait a second. Let's say at this time I got 0. Okay, then at this time height of L is 0 and this is 1, so I got 1. Then I got this height of 2. This time is 0. At this time we will minus, but we will get 1. Count plus equals to math not absolute. All right. Uh, 0. Max of L if smaller than 0. Minimum of this. So at the time of count, we will be adding minimum minimum height. Wait a second. Let's just make it in proper way. So area we will get math dot min of height. We will get the minimum height. The time of this 0 minus 1 we will get GIGHT. Now max of L will be math dot max math.max. Yes. Alright, math.max or maximum of this we will be putting here. Area we already got. So, and we will just simply increase the count by the area we got. Let me tell you what I'm thinking at this time. See, uh, through the algorithm, what we got, how we are calculating the area at this time. Area is equals to minimum uh, minimum of this minus height of L. Okay, so at this time, which one is minimum? This is minimum, so we got 0 minus 1, uh, we got minus 1, so at that time we got the count of minus 1. Now the max L is this. At this time, what we got 1 minus 0, so we got 0, we got added that 0, so it became 0. The count is 0 now. Now, which one is minimum? This one is minimum. Uh, no. So at this time, max L is updated to 1. Still is it is 1 because we have added math.max, right? Now height is this. So h minus 1, this became 1, so we added this uh, this 1. Okay, yeah. So let me show you why it is always this much frustrating. Okay, so when we were this when we were at this one, this uh, index, we got max L, max L to be 0, L to be 0 as well, and at that time count was also at 0. Okay, then we came here. Okay, so at that time, which one is minimum? Max L is minimum and L is 1. L got 1. So at that time, if we have uh, uh, calculated it, so minimum of both of them, which is 0, minus height, which is which will become plus eventually, so it will become 1. Okay, let's see. So at this time it will become 1. At this time, so we need to have it plus. Hmm. Area of L, area of left, and can we do the same part with area of right? 0. and let's return the count once. I don't think this will work, right? Because max of r needs to be updated, then max of r here as well, max of r here as well. So minimum of this, and let's run. So we got 23 as our output. Okay, -5. All right. Hmm. So at this time we get 0. At this time we get 0 as well. And this time we get 0. But at this time we'll get 1. Okay. So we will add it. Then 1, 2, 1, 2, 3, 4. We need one thing to keep add into it, right? Because the formula I am thinking of will just use the height and the length, and it will take its containing water like what we had in this part. It will do that. But here we also need to keep track of these blocks which are there, which are acquiring a unit within that storage of water. So we need to subtract that as well. Can we do something about it? So what we can do is we can say this. Let's say left and right are right is this, left is this. So let's say left is going here. Okay. Got this 0. As it goes down, we will keep decrementing. As it goes up, we will keep incrementing. Can we do that? 5, 1, 2, 3, 4, 5. This makes of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? So at that time, if we will uh, decrement it 1, 2, okay, 2, and what is this? We will add one block, this one. this 2, this 1. Okay, and if we got this, then we will increase the length. I'll add 1. At this time, we have added, we have -1 by 0. At this time, hmm, All right. Given and non-negative integers representing an elevation map where the width of each bar is 1. Yeah, this time we'll get 0 plus 1 minus 1 plus 2 1 0 1. uh, how much is this? So 4. This is 0 1. It will be max, right? Because we need to cut the area. And then the height of this. Add it, and so at that time we will get a count of left area. So let's say we have this, it will become 0, okay, because max of this and height of left is this. Then we will get max of L. Yeah, that will. So we got 7, and here we got 11. Hmm. Oh, so yeah, height is. Let's. Uh, and this time it will be 0. And this time it will be 0 as well. But max of this will be this. Then I'll get 1. Here we will get 1, and This time we will get okay. Math.max. Okay, let's check for this one. Which one is variable? This one is variable, right? So got three here. Uh, let's look for the solution. I thought that I will get the solution like in first 30 minutes, but I'm still confused in the iteration. Not in the iteration as well. I'm still confused that how I will eliminate these units from the contained water. Let's try. Let's go for the hints first. Is there any hint? There is no hint. Big of n, big of space, where n is the size input. Yes. How can we determine the amount of water that can be trapped at a specific position in the array? Perhaps looking at the image might help clarify. Okay, so They have used an I pointer. Why they have used an I pointer? That's why is there a height of I?
Hey everyone, welcome back, and let's write some more NeetCode today. So it's been a while for me, sorry I've been pretty busy, but let's today solve LeetCode 42, trapping rainwater. So we're given an integer array representing the heights of certain elevations or whatever, right? So it's a one-dimensional array. The first value is 0, meaning a height of 0, so that's over here. The next value is 1, so that means a height of 1. Some have heights of 2. This one has a height of 2. This one has a height of 3, right? And so given this entire structure, we basically want to know what's the maximum amount of rainwater could this structure trap, right? Given an unlimited amount of rain. So you can see this is 1 unit right over here. This is roughly 4 units, right? 1, 2, 3, 4, and then this is another one, right? So when you count all of those, you get a total of 6 squares, right? So the output is 6. This can trap a maximum of 6 blocks of water. So with a picture, it's pretty easy, but how do you know, right? Like, what's the algorithm to determine how much each position could trap, right? Like, for example, this position is the first one, right? So there's no boundary on the left of it, right? So no matter how much water we would add over here, it would all just spill to the left. And the same is true for this position, right? No matter how much water we put on top of here, even though there's a right boundary over here, right, there's nothing on the left of it. So all the water is just going to spill out to the left, so it's not going to trap any water. But you can see in the third position, we are able to trap exactly 1 block of water. So what's the algorithm to determine why is it 1, right? Because we care about the height, because we want to know how much water. And it's actually pretty simple, right? Take a look. So here we have 1 block of water. What if I added a second block of water? Well, we can see that there is a boundary on the right. This is good, right? But what about the left side? There's no boundary over here, right? Meaning any water I add is just going to spill out. The boundary only has a height of 1. So we're seeing that the height on the left is 1, the height on the right is 2. So we need to take the minimum of that. We need to take the minimum of 1 and 2 because that is our bottleneck. That is what's determining exactly how much water we are able to trap per position, right? For every single position, we need the max height on the left and the max height on the right, left and right, and then we need to take the minimum of those two. Let's take a look at this position. Clearly we can't trap any water here, but why exactly is that the case? Well, when you look at the right position, right, in the entire right section, the maximum height is a 3, right? So that's good, 3 here. What's the maximum height on the left side? It's a 1, right? This position is a 2. If we take the minimum of 1 and 3, we get 1. So that's our boundary. That doesn't mean we can trap any water here. We can trap 0 water here. The reason is because the actual calculation is we're going to take the minimum. We're going to take the minimum of the maximum left height and the maximum right height. We're going to take the minimum of those two, and we're going to take the height that we're currently at, right? So let's say h of the index I that we're at. So this is the equation we're going to use to determine at every single position I, let's say this is our I position, right? So you can see I is in this equation. This is going to determine how much water we can trap in position I. So we know the minimum of the max of the left and right, right? Because the left was 1, the right was 3. The minimum of those is just going to be 1. And h of I, so the height at position I is 2 over here, right? 2. So we're going to take 1 minus 2. That's actually going to give us a negative number, right? Right, that's going to give us negative 1, but we know we can't trap negative water, right? So we're always going to round up. We're never going to use negative numbers because it doesn't really make sense to trap negative water over here. So really, since the solution is negative, that really means that we can trap 0 water in this position. But let's just move to a couple more positions before you probably get the idea. So over here, right? In this position, the height is 1, right? And the max height on the left is 2. The max height on the right is 3 again, right? So we take the minimum of 2 and 3, so we're going to get 2, right? 2 is the minimum. And height of I is 1, right? The height at this position is 1. So that means we can trap exactly 1 water in this position, right? Clearly, that is the case, right? We're trapping 1 unit of water. And basically, if you did this exact same calculation for every single position, including this position, you'd get the appropriate water count. So this position would give us 2 units of water. This is
Okay, so I got it. Uh, so basically what he's doing is he's iterating left and right pointer. Okay, let's say right is at 1. Okay, so he's doing this. Left is smaller than right, and right is smaller than height of dot length length. So what he's doing uh, is left and right, and yeah. So let's say we have this for int of min height height minimum height of this we have 0, and for int of, let's say this is the iterator x equals to 0, x is smaller than height dot gth x plus plus, and while int of I equals to min height. Okay, not min height, I will be minimum height into L and R equals to 0 and 1. Let's say while L is smaller than R and R is smaller than height dot th dot length for int I equals to L, I is smaller than R and I plus plus. Alright, so let's say first we will uh, get the height. Okay, So we'll see int of area count as well. 0 count will be plus equals to minimum math dot minimum of THAGST of L or GHT of R minus I GHT of I. Okay, and let's take it as area equals to this, and if area is greater than 0, then add area, otherwise 0. क्या हुआ तो यार. Area count plus equals to is greater than this, greater than 0, then area, otherwise 0. Okay, so we have added the added this as well, and lastly we will update the minimum height of L or height of R. And how we are going to update the height? So we got the area, okay, and it happens R plus plus. We'll do this for sure. Okay, but when L will be incrementing, that's the case. So L will get incremented. So if height of R is greater than height of L, at that time L will be placed at R. Okay, so let's say this height of R is greater than L, and L at that time case we don't need to worry about this. Okay, and at this time we can keep it as this as well, and we will keep iterating R, and let's see. Identifier expected, like this. All right, buddy, all right. Let's just keep it simple. We got 7 and we got 15 again. If area is greater than 0, then area will be counted, otherwise it won't be counted. And area will be math height of L, height of R, height of I, count. Bro, no.
Is going to give us 1. These are going to give us 0. This is going to give us 1. And the rest are going to give us 0 water that we can trap. Once we take the sum of all of those, we are going to get our answer 6. So now let me actually show you the efficient ways to solve this problem. Okay, so I'm going to show you 2 different ways to solve this problem. Both of the solutions are linear time solutions, right? So big O of n is going to be the time complexity of the solution, but the first solution I show you is going to actually require big O(n) of memory as well. There's an actual optimization you can do with 2 pointers to reduce the memory from linear memory, big O of n, to constant memory. So I'm going to show you both of the solutions, and it's actually not a lot of code. The code is actually pretty easy. Since for every single position, right, to know how much water we can trap at index I, we need to know what's the max left and right height of every single position, right? So for this position, the max on the left is going to be 2 right over here, and the max on the right is going to be 3 right over here, right? So we're going to need to be doing that calculation a lot. So we can actually make an array and then store that calculation for us so that we only have to do it a single time each. So first we can scan through the array, right? Just go iterate through the entire array, calculating every single max left position, meaning for this position, what's the max height on the left of it? Well, there aren't any heights on the left of it, so it's going to be 0. What's the max height of this? Well, the max height is 0, right? That's the only height that came before it. What's the max height on the left of this? Well, it's a 1, right? So we can do this in linear time, big O of n time. So I'm just going to do that, right? What's the max height on the left of this? 1. Max height on the left of this. We have a new max. It's 2, right? We just keep track of what the current max is so far. Right now it's 2. 2. We got a new height, a new maximum. That's 3. So now 3 is going to be the max left height for the remainder of these, right? So we calculated the max left height. We can actually calculate the max right height pretty easily as well when we iterate through this in reverse order, right? We go from right to left. So initially the max right height is 0 because there's nothing on the right of this. Next it's going to be 1. Now it's going to be 2. And now we got to a 3. So the max right height for the remainder of this is just going to be 3. And remember, we actually need to take the minimum of the max left and the max right for every single position, right? So for this position, we want the minimum of these two values. For this position, right, 0, we want the minimum of these two values, right? Because the minimum is going to help us determine how much water we can trap in this position, right? And clearly, we can actually find the minimum of these two arrays as well in linear time. So here is the minimum is 0, minimum is 0, minimum is 1, 1, 2, 2, 1, and 0. And so now for every single position, we're going to determine how much water we can trap. And we can do that, remember, with our calculation, we can take the minimum of the left and the right and subtract from it the height at position I, right? And we're always going to round up. We always want it to be greater than or equal to 0. And then we can add the sum of all of those values and then get the total water that we can trap. So in this position, we have 0 minus 0 minus 0, right? So here, the amount of water we can trap is 0. Here we have 0 minus 1. That's going to be negative 1, but we don't count negatives, so the amount of water we can trap here is 0. Here we have 1 minus 0, the height at this position, so we can actually trap 1 water in this position. Here we have 1 minus 2, that's going to be negative, so we can't trap any water here. Here we have 2 minus 1, so that's going to be 1. That means we can trap 1 water here. This is 2, so the maximum boundary is 2. Minus 0, that means we can trap 2 units of water here. Next position, we have a 2 minus 1. We can trap 1 water here. Here we have 2 minus 3. That's going to be negative. We can't trap any water here. This is going to be 2 minus 2. Again, 0 water that we can trap here. 2 minus 1, that's 1. So we can trap 1 unit of water here. Here we're going to get 1 minus 2, that's negative, can't trap any water here. Here we have 0 minus 1, that's also negative, so can't trap any water here, and that makes sense. Why would we be able to trap water here when there's no right boundary? But okay, so we have all of our values. We take 1 plus 1 plus 2 plus 1 plus 1, and we get exactly what we expected, right? We get a 6. We can trap 6 units of water here. So this is the solution, taking extra linear memory. Okay, so now I'm going to show you the O of 1 memory solution. It's still linear time, big O of n time, but this time we're not going to need any of this extra memory that we just allocated. We're actually going to do this. We're going to do this with 2 pointers. So initially, I'm going to have my left pointer over here. I'm going to have my right pointer here. So the right pointer is going to be all the way at the end of the input array. So we're going to have our 2 pointers initialized. We're also going to have 2 variables, max left and max right, which are going to be keeping track of the maximum left pointer and maximum right pointer so far. So you can see left is initially 0, so the max so far on the left is 0. You can see right is initially 1, so the max on the right so far is 1. So now we are going to have to update our pointer. Now, which pointer are we going to shift? We're going to take the one that has the smaller max value. So right now you can see max left has 0, max right has 1. So we're going to shift the smaller one, which is left. So we're going to take our left pointer and shift it. So now our left pointer is over here. And just FYI, we know that we can't have any water stored on the endpoints, right? On the left and the right positions, we can't have any water because they're endpoints, right? They can't contain any water. But this position technically can have some water. And how are we going to determine that? Well, we're going to take how much water this can contain, right? We're going to take the max left value that we have in our variable right now, right? How come we don't need the right value? Well, I'm going to show you. So this is the part that you kind of need to notice the trick, I guess, right? So we're in this position, right? Now, remember originally we wanted the minimum down here. You can see we wanted the minimum of the max left and max right. Well, we know what the max left is so far, right? The max left is 0, right? That's what's over here. Now, we technically don't know what the max right is, even though this variable says 1. Yes, so far it's 1, but we know that the max right could actually be 3, right? That's what the true max right is of this position, right? Because there's a 3 over here. So why is it that we don't need that value? Because remember, we want the minimum of the max left and the max right. Now, we clearly know that the max left is 0, right? So it's smaller than what's even at this position, right? And we want the minimum of it. So no matter how big this value is, right? Right now it's a 3, it could be a 10, right? It doesn't matter how big it is because we want the max of the left and the right. And we already know that the left is pretty small, right? It's 0. So it doesn't matter what's in all of these values because we know that the max left is our bottleneck, right? Remember, we shifted our left pointer from here to the next position because left was smaller than right. That's why we shifted it. That's how we're able to calculate the water that's trapped in this position without knowing what the max right is. So with that being explained, let's actually go through this so we can get to the code. So what's the amount of water that we can trap over here? It's actually 0 because the max left, which is the value that we need, is 0, right? So 0 minus what the actual height is in this position is 1. We know that's going to be a -1. We don't count -1s, so we're not going to use that. So we're going to say that 0 water can be trapped here. But you can see, look, this is a 1, right? Our left pointer is here, so we can actually update this. We can cross the 0 out. Max left is now actually going to be 1. So now we're actually at a dilemma, right? Because take a look, our max left and our max right are both 1, so it doesn't really matter which one we shift. Let's just shift the left one again. So we're shifting our left pointer over here now, right? And since they're equal, this is going to be the bottleneck, which is left pointer and the max left, and it's 1 so far. So no matter how big anything over here is, we know that 1 is going to be the bottleneck. We're going to do 1, which is the max left pointer or the minimum of the max of the left and right pointers, right? So we're going to take that 1 minus the value that's in this position, the height of the index I, which is 0. So that's going to give us a water level that is 1. So that means in this position, we can store 1 block of water. So basically, I'm running through the algorithm with 2 pointers. So I'm just going to quickly go through the rest of what this example would be. So again, we're going to shift our left pointer because left and right are equal. So it doesn't matter which one we shift. We're shifting the left one over here. So now to calculate how much water would be stored here, we're going to take the max left pointer, which is 1, and subtract from it the height that's in this position, 2. That's clearly -1. So what we're going to say is that 0 water could be stored here. And so since we reached a height of 2, that means we can update max left and set it to 2 now. So now remember, we want to shift the minimum pointer. And right now the minimum pointer is the right pointer, which is a max height of 1. So we're going to take our right pointer and shift it. And since we shifted the right pointer, now we have to calculate the height or the water that we can contain in this position, right? And so remember, now the bottleneck, right, is going to be this. The max right height for this position is 1, right? So it doesn't matter how big heights over here are, right? There's a 3 here, but we don't care about that because the max right height is 1. And remember, we're taking the minimum of the max left and right height. So no matter what we do, that's always going to be 1 for this position. So we're going to take 1 minus the height in this position, which is 2. That's obviously going to be negative, so we don't have any water here. So we can say 0 water here. And since this is a 2, that means we can also update our max right height now to 2. So this is going to be set to 2 now. The max right height is 2. And since they're now once again equal, they're both set to 2, I'm going to be updating the left pointer because it doesn't really matter which one we do. Okay, so let's calculate the water in this position. So we're at a left position, so we're going to take the max left height, which is 2, minus the height in this position, 1. That's going to give us a 1, meaning that we can contain 1 unit of water. And the height in this position is 1, so we don't update our max left height, but we can now shift our left pointer 1 more position. Now our left pointer is over here. Our max left height stayed the same. It's 2, so let's compute the water we can store here. 2, which is, the boundary, subtracted by the level here, which is 0. So that's going to give us 2 units of water that we can store here. So a 2 here, and let's shift our left pointer again because the max left and rights are equal. So now we're over here. What's the max left? It's still 2 minus the height in this position, which is 1. That's going to give us a 1. So that means 1 unit of water can be stored here. Let's shift our left pointer again. Awesome. So now our left pointer is actually at a 3. So what we're going to do is 2, which is the max left height, minus 3, which is the height in this position. That's going to give us a negative, right? So what that tells us is that we can't store any water here. That's a 0, right? But you can see our max left height can actually be updated now, right? It's going to be set to 3 now. So this is a little bit messy, but let's just say our max left height is 3. Right? And our max right height is still 2. Remember, we're shifting the minimum height. So we're taking now the right height and shifting it. So now we can take, so we're at a right position. We can take the max right, which is 2, subtract it from the height in this position. 2 minus 1 is going to give us a 1. That means we can store 1 unit of water here. Now let's shift our right pointer again because 2 is less than 3. So now we're basically at the last position, right? So the max right height is 2. The height in this position is 2. So what we're going to do is 2 minus 2. That's going to be 0, right? So we can't store any water here. That's going to be a 0. And now you can see we filled in the water levels that we wanted, right? When you take this 1 plus 1 plus 2 plus 1 plus 1, once again, you're going to get the total 6, right? Because 6 is the amount of water that we can store. I just showed you now how to actually do it without any extra memory, right? We took away this big chunk of memory that we were using, and we did it with 2 pointers. And if it doesn't make a ton of sense right now, it might make even more sense when you take a look at the code, which is actually shorter than you would expect. Let me show you that right now. So one short edge case we have to take care of is if not height, meaning the input is empty, we can return 0. This is needed for this problem. And just like in the explanation, I'm going to initialize 2 pointers. Left is going to be at the beginning, so index 0, and right is going to be at the last index, so length of height minus 1. I'm also going to have 2 maxes, so the left max and the right max, which are initially going to be set to height of the respective indices. So height of left, height of right. I'm also going to have a result, which is going to total the water for us. So I'm going to run this loop while left is less than right, so before they meet each other. And remember, we're going to decide which cell to compute and which pointer to shift depending on the comparison between the maxes. So if left max is less than right max, then we're going to be shifting the left pointer. Otherwise, we're going to shift the right pointer. So if left max is smaller, we're going to increment left by 1. In the opposite case, we're going to decrement right by 1. And remember, we're also going to be updating the left max, right? So if we get to, let's say, compare left max with the current height at position left, right? So whichever is greater, we're going to be updating the left max with that value. And we're going to do similarly in the opposite case. So right max would also be updated to the max of itself and the new height that we get to height R. And remember, so in this case, right, we're going to be taking the left max and then subtracting the height at the position I or the position L, right, at the left pointer position, right? So we're going to be making this computation, right? And then we're going to be adding that to the result, right? So this is going to be added to the result. Now, notice how I'm not making any check to check that this is negative, because technically this is never going to be negative. And you can dig into that if you want. It's because I'm updating the left max here before I'm doing this computation. But if you were to swap the order of these two, you would need to make sure that you're not adding a negative to the result, but that's just a minor detail that you can probably confirm on your own. The bulk of this is that you have to take the left max and then subtract it from the height at that current position, right? And so in the else condition, we're going to be doing the opposite. We're going to be adding to the result the difference between the right max and the height at the right pointer. So this is really what I was just doing in the picture, right? This probably makes it a little more clear because we actually have good variable names and stuff. But yeah, after all this is done, the last thing that you have to do is just return the result. Let me just prove to you that it runs and runs efficiently. And you can see that it does exactly that. So I hope.
Amazing. Yup. For how much time we are streaming? Alright, uh, today's stream will be till this time only. It took almost 2 hours to complete. Okay, so tomorrow we will start with the sliding window. Alright, guys, thank you so much.